We are halfway through the spring semester of 2024, and I have to figure out what I'm going to do in the fall semester of this year. Summer semester is already pretty much taken care of because they create some enrichment courses and you have to sign up for it and take that. It's pretty much taken care of for you. But in the fall, you get some options, and you have to figure out what options are best for you. Now, I'm in the unique situation. I shouldn't say unique, I should say a new situation I've never been in before, where I have to figure out when I'm going to do my candidacy exam. So what is a candidacy exam? Basically, you figure out what you want to do your research in, you figure out an approach for it that you and your advisor are in close contacts with, you figure it out. And then you make some sort of presentation, your advisor looks over it, says, okay, it looks good, I give it my pre-approval. And then you take the presentation and you deliver some sort of, presentation, for lack of a better word, to a committee, and they look over it and they say, okay, that looks good. And 40 minutes later, they write out, sign the paperwork and say, boom, this guy passed his candidacy exam, and now he is no longer required to take classes. So if I do that in August, then I won't have to take any classes in the fall. But in case that doesn't happen and I end up doing candidacy later, like in December, I have to figure out what classes I'll take in the fall. Now, there's this one class that's being offered. I'll tell you what it is later. It's 4 credit hours, so I want to take that. And then there's the measure theory seminar, which is 3 credit hours. So in total, that is 7, and I think I need 8. And so what I did was I went to the graduate student coordinator, and I spoke with them and said, this is the situation. I'm trying to figure out what other class I can take that's 1 extra credit hour, so I don't have to, take a really hard class that will take up a lot of my time, because I'm post-qualifying exams. I really would like to take something that doesn't, break my back or anything. And so I suggested, my suggestion was to take complex analysis 2. And he wasn't really a fan of that idea because I've already taken Complex 2. And the reason I suggested it is because I know the instructor. I know what his workload will be like. It's very light. You just do 1 presentation. That's it. And he talks about new material that was not covered in my my previous Complex 2 class. So it's basically a new class. It's called Complex 2, new instructor and everything, but different requirements, different material. So I'm kind of interested in it. But he wasn't really a fan of the idea, understandably, and so he's suggested some new things. So he goes, what about taking probability theory next year? And I was like, I've already taken that. I took probability 1 and 2. He goes, okay, so what about number theory, like analytic number theory? And I said, well, I've taken that as well. And then he just looks at me, he goes, how long have you been here? I was like, almost 3 years. And then he's like, okay, you really do need to pass candidacy and be on dissertation. So that's kind of the goal for me right now, is I want to prepare. I actually worked on the presentation a little bit tonight, just doing basics of what I can. I definitely can't do it this semester, but by the time summer semester is over, I should be able to do it. I think it's a reasonable amount of time to get something done. Now, in the case that I do have to take classes in the fall, the 1 course in addition to the seminar that I want to take is for like the first time in the university's, I don't want to say history, but if this class has been offered before, it's been a really long time since they've offered it, again. So they're offering a graduate level topology sequence next year. And when this was announced, a lot of graduate students that love math were like, oh, they're teaching topology next year? I can't wait to take it. So it was kind of, it's the buzzword right now. It's like, I can't believe we're doing topology. And so I'm interested in it. Obviously, if I end up doing my candidacy and don't take classes, I may just sit in on the class and take notes, just casually learn topology. And I remember making a video a long time ago about my course recommendations in math, and I did not include it on the list. And so a lot of people in the comments were like, this guy hates topology. Why didn't he put it on the list? And it's not that I don't hate the class. It's not like I deliberately left it off. It's just that all the topology that I've learned was embedded within an analysis course. Like, for example, this book talks about it a little bit. This book talks about it at the end. The chapter 3 of this Kolmogorov book talks about it, as well as this book up here that I got from the library talks about topology. And my experience with topology isn't necessarily the best, I admit, but it's not like I hate the class. Basically, before I took any form of topology, I remember hearing that word being thrown around a lot, and it got more and more hyped up. I was like, I can't wait to take topology sometime. I want to figure out what topology is, see what it's all about. I want to know what topology is like. And then eventually, when I was in my measure theory class during my master's program, we had one chapter on topology, and I remember just reading the chapter and being utterly confused the whole time. I was like, this is not what I expected at all. And I just had to reread all the examples just to try and figure out what this class was all about, or what this subject was all about. And it's just, it's like I would feel like I figured out what they were talking about, and then I would read a follow-up example, and it would completely contradict what I thought was my understanding of the subject. So there was a lot of like, nope, you didn't quite understand it, got to go back. Okay, I figured it out. Nope, actually, turns out I really didn't. There was a lot of that. So it kind of soured me on the topic at the time. But that was 5 years ago. Now, when I read through my topology book, again, my understanding of it is very basic. It's a very surface level understanding of topology, but I do appreciate it now. It was a slow burn. I don't know if that's the proper term, but it took me a long time. It's an acquired taste. That's a good way of thinking of it. Topology for me was an acquired taste. And now I'm kind of really interested in getting deeper in it if I can, without, interfering with my research. So what I want to do is probably just talk a little bit about topology. I took these notes from that Kolmogorov book, and I thought it might be an interesting topic to make a video on. I'll definitely go through it when I make the measure theory series of videos, which, there's going to be an announcement soon, but I don't want to do what I did last year and announce it, and then months go by and I do nothing. But whatever. Let's just talk about topology for a second. Let the math speak for itself. Okay, so we have some non-empty set X that's given to us. I think if it's empty, it's still okay, I guess, but it's not really interesting if it's empty. And we denote P of X as the power set of X, which means it's just the collection of all subsets of X. So a topology really is just a family of subsets of X, so you can think of it as a subset of the power set, that satisfies three basic conditions. So what are the conditions? The first one says, the empty set and the set X itself must be elements of the topology. Okay, pretty basic. And then the second one says, if I have a finite collection of elements from tau, so remember these elements are sets themselves. So if I have a finite collection of elements from tau, then their intersection must also be an element of tau. Okay. And then the third requirement says, if I have an arbitrary collection of elements from tau, meaning, finitely many, countably many, uncountably many, it's fine, then their union must also be an element of tau. If these three conditions are met, then tau is called a topology. And then if you endow the set X with this topology tau, then it's called a topological space. That's really all a topological space is. I remember this definition gave me a lot of trouble to understand. It was not a normal way of thinking for me. I don't know what it was about this that just, got me hung up. And by the way, it's not explicitly written this way, but this is what the Kolmogorov book says. I just put it in math language, meaning the symbols and whatnot. And seeing it as the symbols kind of helps me understand the definition more. Now, these elements of tau are usually called the open sets. I say usually because I think some books will call it a neighborhood. I'm not sure what book that is, but I had a teacher that kind of had the word neighborhood and open set flipped, and it really threw off a lot of people in the class. But the Kolmogorov book calls these elements of tau open sets. And it should make sense, because if you've taken some sort of metric space or some sort of class that talks about metric spaces, then you know if you have a working definition of open sets in your metric space, then you know if you take a finite intersection of open sets, you get an open set. And if you take an arbitrary union of open sets, you get an open set. So that's kind of where this definition comes from. Okay, and if we have open sets, we should talk about the closed sets. So a closed set is a set F such that if, hold on, let me read what I've written here. F is closed set if there exists an open set G such that F is equal to X get rid of G, meaning that F is the complement of some open set. And you've probably heard this theorem before once or twice if you've taken a course in real analysis. A set is closed if and only if its complement is open. I think that's more or less a theorem in some textbooks. In some textbooks, it's a definition of closed set. Okay, so now I want to talk a little bit more about other words you hear about in topology. So if you have a given point X in your topological space, a neighborhood of X, which we denote as U sub X, is a set that satisfies the following two requirements. So the first requirement is that X must be an element of its neighborhood. That should be reasonable. And that neighborhood should be an element of the topology. In other words, it's any open set that contains X. You can think of it that way. And so then we have two more definitions, contact point and limit point. So we say X is a contact point of some set A. Now this set A doesn't have to be an element of the topology, it's just any set. X is a contact point of A if for any neighborhood of X, its intersection with A is non-empty, meaning that it contains at least one point. So if you want to think of it in layman's terms, a contact point is a point that touches the set A. So obviously any element that's in A is going to be a contact point of A, but you can touch A without actually being in A. Think of the unit interval, for example, from 0 to 1. If you remove the number 0 and the number 1, 0 and 1 would be contact points of that unit interval, even though they're not elements of the unit interval in that case. That's kind of like the definition I always, or not the definition, but the example I always keep in the back of my mind. But in that example, it's actually stronger. So you have this notion of limit points. So X is a limit point of A if, given any neighborhood of X, the neighborhood intersected with A has infinitely many points in it. So it should be clear from this definition that any limit point is automatically a contact point, but a contact point isn't necessarily a limit point because you have no idea how many elements are in this guy. But here you have infinitely many. And we'll look at some examples that explain limit points here in a second. Okay, and then we talk about closure. So if we have a set A, we can talk about its closure, meaning it's the set of all contact points of A. And that's more or less our rough definition of it. Another way of thinking of it is it's the smallest closed set that contains A. You can think of it that way. Smallest meaning with respect to set inclusion. So that's what we mean by closure. Okay, so for example, we have a couple examples here. I mentioned before the unit interval. If we let X denote the set of real numbers, we can talk about open balls. So BR of X represents the R ball centered at X, which means we're looking at all real numbers that are within R of the point X. So it's an interval in this case. That does not include the endpoints. And we can ignore more or less this part here. I just really want to come down and talk about this. So the open interval from 0 to 1 is an open set. You have to show it's an open set, but it's more or less obvious from the definition. If you impose I'm not saying this very well. if you define B of Rx as the open set, then any arbitrary union of balls is an open set, and any finite intersection of balls is an open set. That's the topology that we're using. So clearly, the open interval 0 to 1 is an open set. Just pick center 1/2 and have radius 1/2 as well. The number 1 is a contact point of the open set, because no matter what open set I draw around it, no matter how small I make the ball around number 1, you are always going to intersect this set. More so, you have infinitely many points in it. So actually, 1 is more than just a contact point, it's also a limit point. And the closure of this interval is given down here, where we include 0 and 1. Okay, so let's look at some more abstract examples. So the first abstract example here is more or less a trivial example, is that if you have a set X that's any set, and P of X is the power set, then if you just define tau to be the power set, then it automatically satisfies all 3 conditions, and we end up with a topological space here. So this is the trivial topology, because you're basically saying that every set is an open set. Obviously, if you say every set's an open set, then it's going to satisfy the 3 conditions. So this topology is not very interesting. In the other extreme case, you can define tau to be the empty set and the set X itself. I had made a typo here, I had to scratch that out. But if you define tau to just be those 2 sets, because then you've definitely satisfied this guy, but it's not too hard to check that these 2 guys are also satisfied. It's pretty much immediate from just looking at it. Then you also get a topological space. But again, this example is not very interesting, because here you've been way too greedy, and here you've been too stringent. Meaning I'm saying every set here is open, but down here I'm saying only 2 sets are open. And that's not very, as I said, interesting. You have to define what the word interesting is, but we like open sets. We like playing with them. Okay, and then in the last example here, we have something more abstract, something a little bit more interesting to look at. We define X to be the set of 2 elements, which we call A and B, and we can figure out what the power set looks like. So the power set's going to include the empty set, the set X itself, and then the singletons. So the set just containing A and the set just containing B. And then we're going to define tau to be the empty set, the singleton set of A, and then X. And we have to verify that this is a topological space, but it's not that hard to show. It automatically satisfies the first condition, but it's not that much work to show that it satisfies condition 2 and 3. In fact, it might be a good exercise for people to do, but it's pretty straightforward. Okay, so if we call this tau our topological space, or if this is our topological space, X comma tau, then precisely these 3 sets are our open sets. Pretty easy to see. So what are our closed sets? So closed sets are complements of the open sets, right? So the complement of the empty set is X, the complement of this singleton is this singleton, and the complement of X is the empty set. So the question now becomes, well, for example, how do you calculate, or not calculate, but how do you figure out what the closure of the singleton set is? So one way that you can think about it is the smallest closed set that contains this guy. But what are our closed sets? Our closed sets are these 3 guys. Clearly, this guy won't contain them because he's the empty set. This guy is completely disjoint from this set, which means that our only option is the set X itself. So the closure of A is the entire topological space X. So this example is pretty basic as well, but Kolmogorov included it because I think it's kind of, at least for me, it kind of taught me a lot about topology. When I was struggling with it, I would think back to this example, basically these 3 examples, to try and get comfortable with it. And eventually I did. So it is a pretty dry subject, I'll say, if you're seeing it for the first time. If we were to put mathematics on a continuum where we have pure math at one side and applied math at the other side, I would usually put abstract algebra on the pure side, like the most pure form, the purest form of mathematics, if you will, because that includes subjects like group theory, ring theory, field theory, all that stuff. But then I started thinking about topology, and it's like, you know what? I think topology, aka set theory on steroids, probably takes the cake in terms of the purest form of mathematics. And it took a long time for me to appreciate, but I do appreciate it now. So if I don't end up doing my candidacy exam in August, I am looking forward to taking this course in the fall.